In this video, we present our work, Sparse Views Near Light, a practical paradigm for uncalibrated point light photometric stereo, that will be published at the conference CVPR 2024. Considering a sparse set of viewpoints with wide camera baseline, the goal is to reconstruct a high-quality 3D model. Because of the high ill-posed nature of this problem, most of the approaches nowadays consider pre-trained neural architectures on existing datasets in order to infer the 3D model. However, this comes with many limitations. For example, currently at least 3 viewpoints are required. The distance between the cameras has to be small, and the quality is still lower than what we can obtain when using many viewpoints. In contrast, we make use of additional data per viewpoint, which consists of different images with different illuminations. And this is referred as photometric stereo. It's a classical approach that takes as input multiple images with different illumination and give as an output a normal map and the albedo, basically the color. In its original form, photometric stereo only considers single viewpoints, but there have been numerous extensions that handles multiple viewpoints. However, they are still facing many issues as described here in this slide. So in order to mitigate those limitations, we propose an end-to-end uncalibrated multi-view photometric stereo framework under a combination of point light sources and ambient lighting. So in our case, the light sources can be located anywhere. They don't need to be far away from the object, which provides more flexibility for the data capture. We express the regions at a pixel p using volume rendering of signed distance field as introduced in the framework VolSDF. This is exactly the same as in NeRF. However, instead of using a neural density field for the geometry, they rather make use of a neural signed distance field, which greatly improves the geometric quality. However, instead of making use of an MLP in order to represent the regions, we rather make use of the classical rendering equation, which allows to obtain a closed form expression. So we ignore the ambient lighting for now, and we just simply consider the point light illumination. And this gives the following expression, where we can see here that the radiance now depends on the light source position P. This model also allows to provide much more constraints on the surface in comparison to a neural model, which is very important, especially in the most sparse scenarios. So here we have the BRDF that basically encodes the material of our object, and here we have the shading. So the BRDF can be itself decomposed into two parts, a diffuse part and a specular part. So this can be visualized properly in the following figures, where we can see that the diffuse part rather corresponds to the true color of the object, and the specular part encodes the specularities. And here we have the visualization of the shading. So in the end, our architecture consists of one MLP for the signed distance field and two MLPs, which represent respectively the diffuse albedo and the specular parameters. And we have here also the light source positions that will be trained together with the MLPs. In order to account for the ambient lighting, we make use of a very simple strategy where we capture an image with only ambient lighting and we subtract it from the other images. And thanks to the linearity of the radiance, this will cancel the radiance that is due to the ambient lighting. This will add a bit of noise in the images, but as we will see later, the results are still very good. Our final loss consists of a data term, the aconal term which ensures that our MLP is indeed a signed distance field, and a mask term which guarantees silhouette consistency. So it consists of the binary cross entropy between the mask value and the sum of the weights in the volume rendering integral. This set here corresponds to the tau brightest observations at the pixel p, which means that we are here truncating the darkest observation at the pixel p. And we can see here in this figure that this allows to mitigate some of the artifacts that are caused by the cast shadows. We also propose a different representation for the diffuse albedo. Basically, instead of writing it as a function of the space with a neural network, we rather write it in the pixel domain. And then in this case, the data term boils down to a linear absolute deviation problem, which can be solved using the iterative reweighted least square. And then we plug in this estimate inside the radiance field equation, and we can simply backpropagate through it using automatic differentiation. In this way, we obtain better results in the most sparse scenario, as we will see later. In the experiments, we first reconstruct full 3D model from 6 viewpoints, and as can be seen in the results, we outperform the relevant baseline both qualitatively and quantitatively. We then reconstruct 3D objects from only 2 viewpoints, and as can be seen here, the optimal diffuse albedo leads to much better results in comparison to our ablation, where we use an diffuse albedo network. Thank you for watching.